This is problem 17-10. The pair of blocks shown in the figure are connected by a light, inextensible cord and are released from rest when the spring is stretched from 600 millimeters. The static and kinetic coefficient of friction are mu sub s equals zero point 0.3 and mu sub k equals zero point 0.2, respectively. If the 5 kilogram block moves 300 millimeters to the left, determine the work done A on the 5 kilogram block by the frictional force acting on the bottom of the block, B on the 5 kilogram block by the spring force, which they give the function for the force of the spring, where the spring constant is 1 kilonewton per meter, and the unstretched length of the spring is L naught equals 250 millimeters. Part C, determine the work done on the 10 kilogram block by the gravitational force, and D, on the 10 kilogram block by the frictional force acting on the bottom of the block. Okay, they're asking for us to find a lot of things, but this problem is not as like crazy as it might look at first. Okay, the hard part is understanding the interactions and like the math of everything. So one of the things they point out here is that this is an inextensible string. Well, what does that mean? It means it doesn't stretch. All right, so non-stretching string will stay the same length the whole time, as opposed to the spring that will stretch. Okay, so that's why they're pointing out the idea that the string is inextensible, an inextensible cord. It's also, they call it a light inextensible cord, meaning it has no weight. Also, the pulley is going to be of negligible mass and it won't create a rotational inertia like we've been calculating for other objects. All right, there's not a whole lot more to really introduce other than to just start working at the math. So let's take a look at this. Okay, so let's write down some of the knowns, like our static coefficient of friction is 0.3, our kinetic coefficient of friction is 0.2. Just as a reminder from Physics 170, notice the kinetic coefficient is lower than the static. That's always the case. So when you're having to push something super heavy, like say a refrigerator or something really heavy inside of a box, it's a lot of times it's hard to get it started, and then you start pushing and then you want to keep going because getting started was hard. That isn't just because you put in the effort and now you've got it moving and there's momentum. It's also that the static coefficient of friction is a higher coefficient. So all of a sudden, instantaneously, once this thing starts moving, the friction force will drop and it'll be easier to push the object. Okay, so that's why we have two coefficients. And they want us to find, so they say the 5 kilogram block moves 300 millimeters to the left. So when they say 300 millimeters to the left, don't forget the first sentence says that the spring is stretched 600 millimeters. So we're starting from a point of 600 millimeters and we're allowing the spring to basically pull the block to the left by 300 millimeters. And then we're going to calculate all of the various works being done by all the different forces. Okay, so part A wants us to find the work done on the 5 kilogram block by the frictional force acting on the bottom of the block. Well, in order to find the frictional force, we need to find the normal force. So let's start with the free body diagram. So we'll have a 5 kilogram block times 9.81. We'll have the tension of the string. We'll have the force of the spring. We will have, since the block's moving to the left, we can pretty safely assume that the frictional force is going to be to the right. And then we'll have a normal force. And that's an N sub 5 and an F sub 5. All right, so mathematically, we want to do what we normally do. Well, we need to find the normal force before we can find the frictional force. So let's do sum of the forces in the y are equal to the normal force minus the weight, which is 5 times 9.81, And the box is not going to move vertically, so 0 for the mass times acceleration of the y. So then that can give us a normal force right away of 49.05 newtons. Okay, and then that allows us to calculate the frictional force as the kinetic coefficient of friction times the normal, which is equal to 0.2 times the 49.05, and that equals 9.81 newtons. So now we can calculate the work done by the frictional force. So the work of frictional force of the 5 kilogram block is equal to the frictional force of the 5 kilogram block times the distance. And they told us that this force is, well, we know the force is going to the right, but the block is moving to the left. So it's going to be the 9.81 times negative 0.3 meters. That's the 300 millimeters to the left. So that's going to equal negative 2.94 joules. So that's part A. Part B wants us to find the spring's force work on the 5 kilogram block. Well, they tell us that the function for the spring is equal to the spring coefficient times the final distance minus the initial distance. And that is also found by doing the integral. Okay, so if the coefficient is, sorry, not coefficient, the spring constant is given to us as being 1 kilonewton per meter, and the length of the spring unstretched is 250 millimeters. Okay, so basically the L naught is 250 millimeters, and the K constant is equal to 1 kilonewton per meter. Then you can also say that the force of the spring is equal to 1,000 x. And x is equal to 0 when the spring is in the unstretched position. So now you can just do a difference between the two distances. Now, we could do this what I would say is the proper way, that the work done by the spring is equal to the negative integral of the initial position and the final position, 1,000x dx, and then this is equal to negative 1,000 x squared over 2 from 0.3 to 0.6. This calculates out to be negative 500 0.3 squared minus 0.6 squared. And that calculates out to 135 Newton meters, or joules. Okay, so that's the amount of work that is done by the spring. The spring is pulling to the left, the block is moving to the left. Therefore, the value being positive for the final work done should make some sense. Part C is asking us to find the work done in the 10 kilogram block by the gravitational force. So we do need to know how much the block weighs. I'm going to go ahead and go to a new page. And we need to do a free body diagram for this block. And then we need to figure out what the normal force is. And then we will find out what the frictional force is. And then we can calculate the work done across that distance. So we have our center of gravity. And there is a 50-degree angle here. All right, then we have our tension parallel to the slope. We have our friction of the 10 kilogram block. We have our normal force of the 10 kilogram block. Okay, and then don't forget that we have motion in this direction. All right, now, if we find that the work done by the weight is the component of the weight in the direction of, or that's perpendicular to the ramp, we can go straight to the equation. So we have the weight, the work done by the weight is the force of the weight times the distance traveled. So what is that force? Well, it is going to be the 10 kilograms times acceleration due to gravity times the sine of 50 degrees. And then the distance traveled is going to be 0.3. However, the component that we are talking about, if we were to do a triangle, is in the opposite direction of the motion. So we do have to put a negative. Right? That calculates out to be negative 22.5 joules. Okay, now we get to the friction force. I got a little ahead of myself earlier saying we need to find the normal and the friction. Forgot that was weight. So the friction force is going to be calculated by the sum of the forces, and I mean, I'll say in the normal. Okay, and that's going to be the component of the weight times, well, the mass times 9.81, but now it's going to be the cosine of 50 degrees, and that will be negative, plus the normal of 10 equal to a 0 mass times acceleration because the block will not leave the ramp. All right, that means that the normal is equal to 63.1 newtons. And then the friction force is going to be equal to the kinetic coefficient of friction times the normal. Okay, and then that's going to calculate out to be 12.61 newtons. All right, now that we know the frictional force, we can multiply that number times the distance traveled by the block. Well, that will be the work done by the friction force of the 10 kilogram block is equal to the friction force times the distance traveled. And that'll be 12.61 newtons times 0.3. But the force is traveling in the opposite direction of the motion. So therefore, we're going to end up with negative, and the answer will be negative 3.78 joules.